continuing 1.7, number 2 there, prove that if n is an integer and 3n plus 2 is even, then n is even using a proof by contradiction. All right. Well, I have to tell you, it can be kind of tricky. It's easy to mix up a proof by contradiction and a proof by contrapositive. I kind of like proofs by contrapositive a little better. I think they're a little cleaner. But I'll show you what, well, I don't know, maybe I'll show you both. Okay, so for this second one, it would go something like this. Suppose n is an integer and 3n plus 2 is even. Okay, and now we're going to prove that n is even using contradiction. Okay, so that's going to go something like this. Suppose, I don't think I used this expression last time, by way of contradiction, and I just like to use the abbreviation BWOC, it's like block. So if you ever see suppose BWOC, that stands for by way of contradiction, that n is odd, right? Okay. I'm going to say comma, i.e. there exists an integer k such that, what does it mean to say n is odd? N equals 2k plus 1, right? Okay, well then what can we say about 3n plus 2? 3n plus 2 is going to have to equal 3 times 2k plus 1 plus 2. Just filling in 2k plus 1 for n. Now remember, 3n plus 2 is supposed to be even. Okay. Well, I think we might have a problem because this is equal to 6k plus 3 plus 2, which is 6k plus 5. Well, I don't think 6k plus 5 is even. Ever. I don't think it's ever even because, look, I think this is a trick we maybe used once. Integers can always either be written 2k or 2k plus 1. Right? Never need to write them as plus 5. Because what you can do with the 5 is break off a 1. And then you can take this thing and factor out a 2. So we have 2 times 3k plus 2 and then add 1, which is what kind of number? Is it even? What is it? It's definitely odd, isn't it? Because it has the form 2 times an integer plus 1. Well, that's a contradiction because we assumed that 3n plus 2 was even. Okay, and the symbol that you see when you arrive at a contradiction is either like this or like this. All right, so that has to mean that that n is even. It's really, really similar a proof by contrapositive, actually, because remember, so we went over contrapositive last time, right? The statement we're trying to prove is that if 3n plus 2 is even, then n is even. The contrapositive would say that if n is odd, that means 3n plus 2 is odd, and that's kind of what we showed. So for certain kinds of proofs, they're really, really almost the same. Okay. So I mean, in the real world, nobody's going to say, okay, you have to do it by contrapositive, or you have to do it by contradiction. It wouldn't matter. But that's the idea behind contradiction. All right. Does that make sense? Kind of, sort of? Okay. Let's see, what else we got? Oh, this is so much fun. It's a little hard to see, but you have it in front of you. So what you're supposed to do with this is kind of study it. Maybe some of you have seen this before. If you've seen it before, don't give it away. You know, it's like when you hear a joke, don't give away the punchline. All right. So this is supposedly a proof that 2 equals 1. All right. Well, that would be big news. So whenever you see something like this, see proof in quotation marks, what they're usually, they're cheating. It's not a real proof. There's a mistake in it somewhere. And so the exercise is to find the mistake. So you start off with 2 positive integers that are equal. And so your first step is to say a equals b, because that was given. And then you multiply both sides by a. So you get a squared equals ab. And then you subtract b squared from both sides. You're allowed to do that kind of thing. And then you factor both sides. A minus b, a plus b equals b times a minus b. You divide both sides by a minus b. You get a plus b equals b. And then because a and b were equal, a plus b is the same thing as b plus b, which is 2b. 2b equals b. You divide both sides by b. You get 2 equals 1. Okay. So unless you're okay with 2 equaling 1, you have to find the mistake. Otherwise, 2 is going to equal 1. All right? So now is your chance to save the world. Where did they cheat? Step 2? Step 3. Okay. Well, let's go through it. So step 2, they multiplied both sides by a. Well, I think that's okay. A and b are positive integers. You're allowed to multiply both sides of an equation by a positive integer. And step 3, you're allowed to subtract any kind of number you want from both sides. Step 4, were they factored? Going from 3 to 4 or 4 to 5? It's one of those. What is it? Where did they cheat? Yeah. Step 5. Going to step 5? Oh, and why is that cheating? Aha! A and b are equal, and that means a minus b is 0, right? And you're not allowed to divide both sides of an equation by 0. You're not allowed to divide anything by 0, all right? And in fact, it doesn't come up all that much when I teach algebra classes, but when they learn, it's called the addition and the multiplication properties of equality. Those are the rules that say you're allowed to add and subtract the same number on both sides, multiply and divide the same number on both sides. There's always a disclaimer included that you're allowed to multiply or divide both sides by any number that's not 0. Okay? And yes, that is exactly where the cheat happened. You cannot divide both sides by a minus b. because a minus b is 0. Good.
Wait, so the logic behind that is, so the reason why you can't do it is because, would it be something like how if that would allow you to be able to pretty much turn zero?
Yeah, yeah. You can make weird, crazy things happen if you divide or multiply by 0 on both sides. Yeah. Yeah, this is what you can't do.
If I had the money, I would hire a math to make a new branch of mathematics.
People do it. People do it. That's what some research mathematicians do. They literally create new kinds of math where they can figure stuff out. I mean, at some point, I don't know when this happened exactly. I wish I knew, but somebody came up with the idea of complex numbers. And complex numbers are actually very useful. They use them in engineering. Okay. I kind of hate that they're called imaginary. It sounds like fairy tale stuff. It's not fairy tale stuff. They're actually good for something. All right. Is that it? Oh, okay. So, you know what? I think this might be a good thing to do a little bit later, like maybe around the midpoint, of class, is that I was going to turn you loose on these for a good, 20 minutes or something, maybe around 1:40. I'll have you work on these, and we'll see if we can go over at least, a few of them. All right? So we'll come back to that. That'll be a good halfway through class thing. I'm actually feeling kind of sort of optimistic that we might finish Chapter 1 today. That would be really cool. Okay. So then if you were already logged into Blackboard, you may or may not see these notes. If you don't see them, well then just log out, log back in, and then you'll see them. 1.8. So a little more about proofs. Different kinds of tricks with proofs. Okay, starting with exhaustive proof and proof by cases. So the first one says, prove that there are no positive perfect cubes less than 1,000 that are the sum of the cubes of two positive integers. All right, well, this would be an example of an exhaustive proof, because perfect cubes less than 1,000, there aren't that many of them. There's only 9 of them, I believe. All right. Okay, so all you have to do with that, you know what? This would be a really cool thing to run. You could write a little computer program that would do that. Okay, so perfect cubes are numbers that can be written as the cube of another number. So the first one is 1, because that's 1 cubed. The next one is 8, because that's 2 cubed. And then you just keep going. So it's saying that as long as this number is less than 1,000, you will not be able to break it up into 2 smaller perfect cubes. So in other words, for the equation a cubed plus b cubed equals c cubed. Yeah.
Oh, I'm sorry. I misread.
Oh, you got it now?
Yeah.
Okay. It's basically saying that this equation is not going to have any solutions where c is less than 10, because 1,000 is 10 cubed. So it's a very mini example of something I'm going to talk about later. It's a very special case of something. There you go. I was going over my notes, and I saw, oh, we're talking about Fermat today, and I was a little disappointed that I had forgotten something having to do with that, but I came up with what I think is the next best thing. Okay, so exhaustive proof, basically it's just saying you cannot have any two numbers in this list add up to any other number in this list, is what it's saying. All right? So if you put a 1 here, that's not going to work because the two smaller numbers have to be positive. They have to be positive perfect cubes. Well, the only way I can think to write this is 0 plus 1. But 0 is not positive. It is a perfect cube, but it's not positive. Right? Then you look at 8. Well, the only other smaller numbers in the list are 1 and 1, and they don't work. 20. Then it starts to get a little bit more interesting. 27 is not 1 plus 1. It's not 1 plus 8, and it's not 8 plus 8. Right? And then you just keep going like that. 64. Well, the biggest you can make two of these smaller numbers add up to is 54. 64 is bigger than 27 plus 27. And so if you can just write a sentence that says the sum of two smaller perfect cubes can't be any more than 54, well, then you don't have to show anything with the 8 and the 1. Right? 125 is not 64 plus 64, and it is bigger than 64 plus 27, which is the next biggest thing. I'll tell you what, for any of these exhaustive proofs, if you want to write a little computer program that'll just run through these real quick, I would be totally fine with that for your homework problem. I think that's a really nice way to do it. I actually tinkered with that a little bit. Was it the last? It was one of the last times I taught the class before last year, like way back in 2004 or something. And it was actually kind of fun. And I'm not a programmer, so I had to sit there. I remember one day on a Saturday sitting at my dining room table with my laptop, kind of pulling my hair out, trying to make my programs work. All right. You get the idea? I'm just going to say etc. You will never get any of these numbers to add up to two smaller numbers. I'm saying that backwards. You will never get any two of these numbers to add up to a bigger number that's on this list. That's what it's saying. And it actually turns out that you can't find any three integers that make that work. It doesn't matter if they're less than 10 or not. You could go up to 1,000,000 and you won't find any. And that's part of what's called Fermat's last theorem. All right? Talk about that a little bit later. Okay? Now, you really shouldn't say etc. when you're doing this in a homework problem. You should, do it completely. They're only making you do it up to 1,000, and that's really not that much. Okay? I'm doing it because I think you have the idea, right? Right? I see one head nodding. Yeah.
So you add the preceding number?
It doesn't have to be the preceding number. So what they're asking us to prove is that there are no positive perfect cubes less than 1,000, so these numbers here, that are the sum of the cubes of two positive integers. Now, the two cubes that you're adding together would definitely have to be smaller, right? Because everything is positive. All right. So, for example, here I'm saying, I could have just said, you know what, let me clean this up a little bit. Here I could have just said that 27 is bigger than 8 plus 8. Okay, and so 8 plus 8 doesn't add up to 27, and no numbers that are smaller than 8 that are perfect cubes will work either because they're going to make that even smaller. And then 64 is bigger than 27 plus 27. Now when I get past 64, I don't get off the hook quite that easily because like 64 plus 64 is not smaller than 125. It's actually bigger. It doesn't add up to 125. So I have to say those two don't add up to 125. And then the next smallest thing, 64 plus 27, is too small. Right? And then, you know what, I'll throw in one more. 216 is not 125 plus 125. And 216 is bigger than 125 plus 64. So 125 plus 125 doesn't work. 125 plus 64 doesn't work. And because of the greater than, nothing smaller than 125 plus 64 is going to work either. That's kind of what I'm getting at. Let me see. I think when you get up to 343, oh no, it'll still work for 343, just barely. 216 plus 216 doesn't add up to 343. 216 plus 125 adds up to 341, doesn't it? Oh, that's a close one. All right. But it's just a little bit too small, and so anything smaller than that won't work. I bet when you get to 512, you might have to check maybe one additional one. 343 plus 343 is too big. And this is also too big, 343 plus 216. The next biggest thing is 216 plus 216, which is too small. Okay? So as you go up, you might have to check just a couple more, but you really don't have to check that many. Okay? That's called an exhaustive proof. All right. What do we got next? Got time for one more, and then we'll do our little activity. Oh, I love without loss of generality. That's a lot of fun. Prove using the notion of without loss of generality that 5x plus 5y is an odd integer whenever x and y are integers of opposite parity. Remember, parity means same parity. It's a nice computer science word, right? Same parity means both even or both odd. So the parity of an the parity of an integer is like its evenness or oddness, right? Okay, so opposite parity means one even, one odd. So without loss of generality refers to okay. Well, if we wanted to be extra paranoid and cover all our bases, what we might do is break this into two possibilities. One possibility is x is even, y is odd. The other possibility is x is odd, y is even, right? Well, the idea of without loss of generality is that you only have to do one of those, all right? So it goes something like this. Suppose without loss of generality, okay, so remember block by way of contradiction. Without loss of generality is W log. W-L-O-G. All right, that, let's say x is even and y is odd. So the idea of without loss of generality is just, let's say I get through this part of the proof and I convince you that in that case 5x plus 5y has to be odd. And somebody says, but Mitchell, you're not finished. What about the case where x is odd and y is even? And I would just point to this and I would say, okay, well, run the proof again and just have the numbers x and y trade names. and the proof works exactly the same way. That's without loss of generality. It is yet another way for mathematicians, and I understand this is something we have in common with computer scientists. We're lazy. We like to do as little work as possible, right? And so if we don't have to do it for both of those cases, then we won't. Okay? All right. So that means, I hate starting a sentence with IE. I think it looks weird. Do you know that IE means that is? People sometimes use it. They mistakenly use it to mean for example. For example is e.g. That is IE. And a cute way I remember reading to remember that is think of e.g. as standing for examples given. That's not what it stands for. It stands for some Latin thing. But that's a way to remember it. Okay, there are integers, and I have to use two different ones. There are integers, let's call them m and n, such that x is equal to, x is even, right, 2m, and y is equal to 2n plus 1. Right? Then 5x plus 5y is equal to 5 times 2m plus 5 times 2n plus 1. And what is that? 10m plus 10n plus 5. Oh, and this same exact trick came up in another problem. That is definitely odd because you can break off a 1 and factor a 2 out of the rest. Two times 5m. I know you can factor out a 10. No, you can't. Never mind. You can factor a 10 out of those two. That doesn't do me any good. You want to factor it just like that. You want to show it being written in the form 2 times an integer plus 1. And that's odd. And because of without loss of generality, that's it. That's all you have to prove. Because again, if it's really x that's odd and y is even, you can just switch the names y and x. And it works the exact same way. Does that make sense? Questions? Yeah.
Would it work for subtraction too, or just?
It would work for subtraction, I think. Right? In other words, 5x minus 5y would have to be odd. Yeah. Because then this would be a minus. Oh, you know what? That brings up a really great thing. Suppose it was minus. Five x minus 5y would be 5 times 2m minus 5 times 2n plus 1. That's going to come out to 10m minus 10n minus 5. Now, when you're going to show that that integer is odd, you still need it to end in a plus 1. So you have to be a little sneaky. Because I could see, I bet more than half the class would break that into a minus 4 minus 1. Well, maybe not more than half, but a lot of people would do that. But what you should really do is break it into minus 6 plus 1. Make one of the terms a plus 1. And then you're able to write it in the form 2 times an integer plus 1. So yeah, that's a great point. 5x minus 5y would also be odd.
determining whether it's odd or even,
Mm-hmm.
the goal is, the number that's left outside determines the odd or even.
The number that's left outside, that's right. If you're able to factor a 2 out of the whole entire thing, then it's even.
And if a 2 is left outside, it's even.
Well, but then you shouldn't have to leave a 2 outside, right? Because you could factor a 2 out of that. An even number can always be written as 2 times something, period. And an odd number can also always be written as 2 times something plus 1. Has to be one of these. All right. So I am going to turn this off. Okay, here we go. All right, going over these group problems. Okay, so we want to show that the product of 2 rational numbers is rational. How about somebody other than one of the people who nailed it or came close? Somebody else tell me, what is a rational number? A fraction, right? So why don't we say let x and y be rational numbers. Be rational is one word. That means there exist integers. I need 4 of them. And you're going to see why I need 4 of them in just a second. So I'm going to call them m, n, p, and q, such that x is equal to m over n and y is equal to p over q. Okay? So x and y are rational. So we want to show that x times y is rational. Well, guess what? X times y is just m over n times p over q. Do you know how to multiply fractions? Everybody say yes. M times p over n times q. Is that rational?
Yes.
It is because
It can't be 2.
some, x and y are rational. There you go. Excellent. So in order to convince somebody this is rational, all you have to do is convince them that m, p, and n, q are both integers. Well, the last time I checked, an integer times another integer was an integer. And that's all there is to it. See? Pretty simple. Anything that has the form, prove that the sum of 2 of these things or the product of 2 of these things is another one of these things, they're usually pretty simple. You just use the definition of what is that thing, rational, even, odd. All right? Those are the big examples right there. I can't think of another one right off the top of my head. Yeah? In other words, if you took out the word rational, the product of 2 numbers is rational. Yeah, you wouldn't be able to do that, right? Because then I guess the numbers could be any kind of numbers. Yeah, so we need to know that they're rational, those 2 numbers. Otherwise, it doesn't work. All right. So I heard lots of people talking about B, and somebody told me, and I had this same thought. It's kind of... If you think about it for just a couple minutes, you can start to see why B is true, but it's very hard to find a good way to say it, right? Well, in I want to say chapter 5, we're going to learn about something called the pigeonhole principle. And that'll make this problem really, really easy. Okay? But there's a way to do it even without that. Okay, so here's what I thought of for B. Okay, so we're trying to prove at least 3 of any 25 days chosen must fall in the same month of the year. Okay. All right, so I was kind of thinking of a contradiction type thing. And so here's what I was thinking is suppose not. Now let's think about what suppose not means. All right. It is not the case that at least 3 of any 25 days chosen must fall in the same month. Well, if you don't have at least 3 of something, what do you have? You have at most 2 of something. I.e., suppose at most 2 days fall in any given month. Well, then how many total days could you have if you can only have up to 2 fall in any given month? You could have at most 24. Isn't that right? Then there are, at most, there might even be less, at most 24 days to choose from. Because you could have 2 in January, and 2 in February, and 2 in March, and 2 in April. Two times 12 equals 24. And that's sort of a contradiction because they said you have 25 days. So if you have 25 days, then, here's another way to look at it. Just imagine that you put 2 in January, 2 in February, and 2 in March, et cetera, et cetera. And after you do December, you got 1 day left over. Well, where's that day going to go? It has to go in with 2 of the other days, right? So that's a contradiction. Okay, contradicts that there are 25 days. Okay. I don't feel like we have to go over every single one of these right now, but I was thinking, well, you know what? Yeah, I was actually just about to go over letter D, and I was going to leave letter C to go over on another day, like maybe next time. But now, you know what? I think I'm going to actually leave both of these. So now that you've seen a couple more examples, maybe you'll have an easier time, doing at least one of those, let's say. All right? Okay. You have plenty of time to get all this stuff together, in terms of homework. So I'll be collecting, the remaining Exam 1 homework on the day of the exam. And by the way, the exam covers Chapter 1 and then 2 sections from Chapter 2. And then after Chapter 2, I think you take over for a little bit to do, what is it that we do in Chapter 3, algorithms or something? Okay. And then, okay, so the first exam is Chapter 1. And so the homework I'm going to be collecting the day of Exam 1 is 1.5 through 1.8. So that's 4 sections. And then 2.1 and 2.2. So that's a total of 6 sections. That's a lot of stuff. So I was about to say, I hope that you're finished or pretty close to being finished with 1.5, 1.6. If you're not, you want to get that out of the way ASAP. All right? So that you can work on this proof stuff. All right? But now you have plenty of time to get the proof stuff together. And I didn't really assign a lot of it. All right? Okay, so let's leave C and D. If I forget, next time, can somebody remind me? Go over C and or D. All right? That sound like a plan? So that brings us back to 1.8. Okay. All right, so letter C. Letter C is kind of similar to letter A. Prove that there are no solutions in integers x and y to the equation 2x squared plus 5y squared equals 14. Okay. Well, this would be another example of an exhaustive proof because there really aren't a whole lot of possibilities for x and y. Think about what could x and y possibly be in terms of getting a total, that's in the ballpark of 14. Think about that for as long as it takes me to erase this. Okay. So we got 2x squared plus 5y squared equals 14. All right. Worst case scenario, suppose that y is 0. Now, everybody appreciate that x squared and y squared have to be greater than or equal to 0. And that's really, really helpful, right? Okay, well that means, doesn't that mean that, for example, 2x squared has to be less than, we'll say, or equal to 14? In other words, worst case scenario, y is 0. Well, then 2x squared would be 14. If y is any number other than 0, well, then this number, y squared, is going to be bigger than 0, and that's going to force 2x squared to be smaller. Isn't that right? Nod or shake? Nod. All right. Okay, well, if 2x squared is less than or equal to 14, remember we're talking integers. That means that the absolute value of x, remember x itself could be positive or negative. So I'm going to talk about the absolute value of x. Has to be either 0, which would make that 0, 1, which would make this 2. Let's see, if x is 2, this would equal 8. And I think that's it. It has to be 0, 1, or 2, doesn't it? Okay. And by the same sort of logic, 5y squared has to be less than or equal to 14. Doesn't it? Worst case scenario, x is 0. If x is 0, then 5y squared would be 14. If x is anything other than 0, 5y squared would have to be smaller than 14. So the absolute value of y has to be either 0, 1, and that's it, right? If y was 2, then 5y squared would be 20, and that's already too big. So absolute value of y has to be either 0 or 1. Oh, well, that's easy. I suggested you could write a computer program to do letter A. This you could do by hand much faster than you could write a computer program, I think. Computer program would be good for something like this if this number was bigger. Right? I don't want to throw a number in there because my luck it would be something where you can find solutions. Right? So I remember last year I did something like this. I just made a little table where we talked about what was the value of 2x squared plus 5y squared. this up a little bit. Put a title on the table. So this table is value of 2x squared plus 5y squared. And actually, I should make this be absolute value of x, absolute value of y. So if x and y are both 0, well, then 2x squared plus 5y squared would be 0, which is not 14, right? And if x is 0 and y is plus or minus 1, then 2x squared plus 5y squared would be 5. If x is plus or minus 1 and y is 0, then this thing would come out to 2. See what I'm doing? All right, you just go from there, and you will never get a 14 in any of those boxes. This would be a 7. This would be 8 plus 0, which is 8, and this one here would be... This one's going to be too big, isn't it? Oh, no, it's not. It's going to be 13. All right. So 2x squared plus 5y squared is never 14. And if you use an x or a y that's bigger than any of those, you're going to get something that's bigger than 14. That's what we took care of over here. And that's it. So nice simple example of an exhaustive proof. You just show there's only a few things that could possibly work, and now I'll show you that none of them work. Make sense? All right. Is there one more on here? I think there might be. Ah, okay. I remember, because us math people, we notice things like this. I remember at some point, before I learned how to prove it, noticing that there was a pattern in perfect squares. I don't think I knew how to prove it at that time, but I noticed it. The final decimal digit of the square of an integer. So we're talking perfect squares. Okay? So let's say you've never thought about that ever in your life, and you don't know what they're talking about. Well, look at some perfect squares. So they go 1, 4, 9, 16, 25. So far we've actually hit 5 different final digits, right? 1, 4, 9, 6, 5. But then what happens? It actually is. It actually is. Oh, yeah. Yeah, we should throw 0 in there. We're going to hit it anyway, eventually. Okay. But as soon as you pass 5, they start to wrap around, and you get 36. So there's the 6 again. And there's a 49, there's the 9 again. And then a 64, there's the 4 again, and then 81, and then 100. All right, so it went 0, 1, 4, 9, 6, 5, and then it looped back 6, 9, 4, 1, 0. And if you go and look at the next few, you find that same pattern just repeats again. You know what? It would have been nicer to write it. Actually, what would have been, well, okay. Yeah, that's fine. I'm going to put 100 over here, because then it goes 121, 144, 169. So you notice there's a few that we're not hitting. Like, I don't think we ever got a final digit of 3 or 2 or 7, right? So the conjecture, remember a conjecture is like a guess. The conjecture might be that the final digit is always 0, 1, 4, 5, or 6, or 9. It's never 2, 3, 7, or 8. Okay. Well, oh, okay. All right. So now we're trying to let's be a little more specific about this. So the final digit of the number n squared is always 0, 1, 4, 5, 6, or 9 for all integers n. All right, so now we're trying to prove something for all integers. Well, I don't think an exhaustive proof is going to work for that, because we're never going to exhaust all the integers, right? There's an infinite number of them. So this is going to be an example of a proof by cases. Now, proof by cases, the most common kind of proof by cases is you make a statement about all integers, and you can show that, for example, okay, first suppose the integer is even, da-da-da-da-da, and next suppose the integer is odd, dun-dun-dun-dun-dun, all right? That's probably the most common kind of proof by cases. That is not going to work for this. Okay. So since we're talking about, I think the way we're going to have to do it, and I think what I'm going to do, A, because I'm lazy, and B, because I don't want to take up a whole bunch of time, is so digits in numbers, like the ones digit, the tens digit, hundreds digit, is very like base 10 specific. Okay? So the cases are going to be we're going to look at all the integers n, and we're going to sort them by what is their last digit. All right? So I'm going to do like the first only 2 or 3 of these, because unfortunately this has a lot of cases. So let's make case 1 the last digit of n is 0. And so the other cases are going to be it's 1, it's 2, it's 3, it's 4, it's 5, etc., etc. I was trying to think just now of a shorter way to do it, and I don't think there is a shorter way to do it. Okay. So then, if the last digit of n is 0, that means n is a multiple of 10. Right? 10, 20, 30, 40. N is equal to 10 times k for some integer k. Right? And now you look at n squared, which is the square of 10k, which is 100k squared. And I can show you that that number is also going to end in a 0, because it's equal to 10 times 10k squared. So if n is a multiple of 10, then n squared is also going to be a multiple of 10, and that means it's also going to end in a 0, which is a multiple of 10, and therefore ends in 0. All right. Okay, 1 down, 9 to go. Because the other cases are it ends in 1, it ends in 2, it ends in 3. Okay, I am going to skip ahead. I was going to show you next the last digit is a 1. But I think you might get a little bit more out of, let's say the last digit is a 4. I think I want to skip to 4. So that's 1, 2, 3. Okay. And then I'm going to leave the rest for you to fill in. All right. So then case 5, once we got there, would be the last digit of n is 4. So numbers like 14, 24, 574, all right? And what they all have in common is that they can all be written as 10k plus 4. So it's a multiple of 10 plus 4 for some integer k. I'm feeling really, really lazy now. I don't think I ever showed you guys. How could I have shown my college algebra class and not you the different abbreviations for the sets of numbers? Where can I put it? Right here. Well, the one we use most often in here is integers, and that's this funny-looking letter Z. And that comes from a German word for to count. The German word for count, like counting, is this word, I think. So that's where the Z comes from. Those are integers. Rational numbers are Q, as in quotient. Wanted to say rational. And then real numbers are R. That's a good reason why we don't use R for rational. Okay? So instead of saying for some integer k, I'm going to say this, for some k element of integers. I'm lazy. Gets me out of a little writing. Okay. It's funny. You almost never see these letters written like this, and when you see them in a book, they're just boldface. You see them written like this. The tradition of writing them like that came from, it's very hard to write boldface with a pen. It's very easy to write boldface on a computer. I don't think I've ever even seen those symbols in Equation Editor. I don't know that I ever looked for them, but probably just a boldface Z. Okay, well then, n squared, if n is equal to 10k plus 4, that means n squared is the square of 10k plus 4. And I hope you're all comfortable with the square of 10k plus 4 is 100k squared plus 80k plus 16. And what I want to try to convince you is that that number will always end in a 6. And the reason it always ends in a 6 is because you can break this 16 into 10 plus 6. It's kind of like what we do to show that numbers are even or odd, mostly odd. Break this into 10 plus 6, and then factor a 10 out of those first 3 terms. So this number is 10 times some integer plus 6. And so that ends in a 6. The last digit of n is 4. If the last digit of n is 4, then the last digit of n squared is 6. Right? Because the conjecture was it always ends, n squared always ends in 0, 1, 4, 6, or 8, or 9. Right? 0, 1, 4, 5, 6, or 9. So what this shows is if the number n ends in a 4, then the number n squared ends in a 6. And you can see that if you just do some examples, right? 4 squared is 16. 14 squared is 196. I think 24 squared is 576. Right? Always ends in a 6. All right. So then the proof is complete once you do the other 8 cases. n ends in 1, 2, 3. Those are the ones I skipped. And then you also have to do n ends in 5, 6, 7, 8, or 9. I wish I could think of a shorter way to do that, but I really don't think there is one. All right, that kind of sort of makes sense. So that's an example of a proof by cases. All right. Well, we'll come kind of sort of close to finishing this today, maybe. Oh, this is so much fun. I love this. Prove or disprove that if a and b are rational numbers, then a to the power b is also rational. So here's another one of those prove or disprove. So that they're hard because you have to first decide, do you believe it's true or not? I should give you like just a minute and a half to think about whether you think that's true. If you think it's true, then you have to figure out how are you going to prove it. If you don't think it's true, well, you get off the hook a lot easier. All you have to do is just give me what we call a counterexample. A counterexample would be, okay, so the statement says, if a and b are rational, then a to the b is also rational. What would the negation of that say? So a and b rational implies a to the b is rational. If that's not true, okay, remember how the negation of the statement P implies Q? Oh, I have to tell you guys about my new challenge. So last week I started, did I ever mention I teach at Stanislaus also? So last week I started teaching a one-night-a-week class. It's called Excursions into Mathematics. It's math for people who aren't into math, basically. A lot of colleges call it Survey of Math. Anyway, I decided for their first chapter we were going to do logic, just like basic truth tables. And so when I saw this, I was like, oh boy, here we go. Their book uses a different symbol for negation. Their book uses this, which I think I told you about, that's a symbol that some other books use. So now I have to keep it straight depending on which class I'm talking to. All right, you guys use that one. They use that one. All right. The negation of P implies Q. Remember, P implies Q is equivalent to not P or Q. And by De Morgan's law, that's equivalent to P and not Q. So the way that you disprove a conditional is to prove that the premise can be true while the conclusion is false. Okay? So if you want to disprove that, you have to come up with two rational numbers where a to the b is not rational. It's irrational. Okay. I kind of feel like taking a vote. So how many people think this statement, if a and b are rational, then a to the b is also rational? How many people think that's true and we should prove it? Okay. Everybody has to vote for one or the other. I'm going to come after everybody who doesn't vote. All right. So it looks like this side of the room is really... Okay. How many people don't think it's true and we should disprove it? I don't think anybody in this row voted. Nobody in this row voted. Okay, well, it looks like prove is winning. There are, I think, more people that want to prove it than disprove it. Okay, well, what is, name an irrational number. The square root of something. Yeah. square root of 3. We actually proved, we've proven that exactly one number is irrational, right? We proved the number square root of 2 is irrational. Do you know another way to write the square root of 2? 2 to the 1/2. There you go. This is not a true statement. There's a counterexample. So I think I would like to disprove this, because that's a lot easier, and also it happens to not be true, which is a bonus. Okay, and so the counterexample is let A equal 2 and B equal 1/2. They're both rational. A to the B is 2 to the 1/2, which is the square root of 2, and oh, guess what? We proved that's irrational. You don't even have to take my word for it. Okay. All right, so if you can find a counterexample, find a counterexample, because then you don't have to write a proof. All right, and this, I enjoy this even more. So this is an example of what would be called a non-constructive existence proof. So let me explain what that means. So an existence proof is you're just showing something exists. There is an example of something or other. Non-constructive means I'm not going to tell you what it is. All right? There is an example of a number that does this, but I'm not going to tell you what it is. And yet you're still going to be convinced that the number exists. Okay? And so here's how we're going to do that. I think they go over this example in the book. This is another one of those where normally I don't go over the book's examples because I figure you can read them, but I just couldn't resist this one. Show that, okay, so in the first example we proved that two numbers can be rational and then 1 to the power of the other is irrational. Now we're going to prove that you can do an irrational to an irrational and have the answer be rational. Okay, so a rational to a rational can be irrational. And now we're going to show an irrational to an irrational can be rational. Okay. And here's how you do it. Remember, it's non-constructive. I'm not going to tell you what the example is. I'm going to do the next best thing. I'm not going to tell you what the example is, but I'm going to tell you that either this number or this number does it. All right? Look at the number square root of 2 to the power square root of 2. Now, I have no idea whether that number is rational or irrational. I bet it's probably irrational. Okay? But I really don't know. I definitely couldn't prove it either way. Okay? So if you're okay with not knowing whether that's rational or irrational, I'm definitely okay with that. We'll do it by cases. Let's start with the fun case. If this number is rational, then what? We're trying to show that an irrational number to an irrational number can be rational. We're trying to show that can happen. Well, if that mystery number, radical 2 to the radical 2, is rational, what does that mean in terms of my proof? It's done! It's done! Then that's the example. Okay? But I am not prepared to prove to you that that number is rational. I have no idea. It probably isn't. Okay? So we have to consider the other possibility that it's irrational. Okay, and now I'm going to say, look at this. Look at square root of 2 to the power square root of 2, and then raise that number to the power square root of 2. Trying to show that an irrational number to an irrational power can be rational. Well, if that number is already rational, then we're done. If it's irrational, then this is our example right here, because this is irrational, and this is irrational. And what does that expression simplify to?
2.
To 2, right? Because radical 2 times radical 2 is 2. And radical 2 to the power 2 is 2, which is definitely rational. Okay? So that's why it's a non-constructive existence proof. All right? It's non-constructive because the example of an irrational to an irrational being rational is either this or this. I can't tell you which one, but I can tell you one of those does it. All right? And it's, well, existence, that part's probably a little bit more clear, right? Just trying to show that something can happen. Yeah, it can happen. It happens either this way or this way. Isn't that cute? I just love that. All right? And the best part about it is that it's using the one and only number that we have ever proven is irrational, square root of 2. If you're okay with irrational numbers that we haven't proven are irrational, I know for a fact that the number e is irrational. That's been proven. It was proven in the, I want to say, in the 1800s. I think I've seen the proof once. It's kind of difficult. I don't think I've ever seen a proof that natural log 2 is irrational, but I believe it. That's a constructive example right there. All right. As long as you believe that E and natural log 2 are both irrational. I think they are. I know E is. Pretty sure ln of 2 is. Okay, but this is almost better because we've actually proven square root of 2 is irrational. All right. The downside is it's not constructive. But hey, it's either one or the other. All right. Okay, almost done with 1.8. We will very easily dispense with it early next class.